Before we talk about those specifically, I've kind of referred to this linear grayscale a couple of times already. If you did a quick search on your computer or your smartphone for the normal sonographic appearance of a tendon, there would be no lack of research articles that would pop up for you to review. We know precisely what the anatomy is supposed to look like on an ultrasound image. We know the normal has been well established. And so that's where we're going to start. As such, knowing that normal sonographic appearance, there's really only two ways for the anatomy to deviate from normal. And this is where I like to qualify that I don't oversimplify nor will I overcomplicate this, but with our work that we do, there's really only two ways for the anatomy to slide up and down that scale. So remember we talked about the returning amplitude of those echoes with the pulse echo mode? So if the structure is sending back stronger echoes than we would anticipate if it was normal, if we were identifying a brighter hyperechoic tendon than we should identify if it was normal. Basically, what we identified is a tendon that is probably calcific, fibrotic, or perhaps a foreign body. So anything in musculoskeletal imaging, we identify anatomy that is hyperechoic. You're looking at calcification, fibrosis, scarring, or perhaps foreign body. If it goes down the scale, and that anatomy is being displayed as something that is too dark or hypoechoic, sending back weaker echoes than it should. It means it's softer, it's less dense than we would anticipate, again, if it was normal. And if it's a hypoechoic structure when it shouldn't be a hypoechoic structure, one of two things is happening. One, the structure is taking on fluid, it's edematous, or because it's musculoskeletal anatomy, striated fibrous anatomy, is it not? Poor visualization or non-visualization of that anatomy on ultrasound leads us to the determination of partial thickness tears to full thickness tears and ruptures. Okay? So down the scale, edematous, poor visualization of the normal anatomy, which we're going to be getting to that, partial thickness to full thickness tears, brighter hyperechoic representation of the anatomy, scarring, calcification, fibrosis, or perhaps foreign body, even surgical hardware. So let's get to the meat and potatoes of it here. Bony cortex, this is where it all starts. This is the first thing your eye tracks to when you place the probe on the patient. Bright, hyperechoic, echogenic, smooth, and intact is what the bone should look like, correct? So obviously on this ultrasound image you can see bright, hyperechoic, smooth cortical bone except for right here where that arrow is. There's a disruption in that cortical bone. That is a nice representation of two things. One, in reality, it's an avulsion of the distal fibula from a very strong inversion ankle injury. So when the ATFL ligament gets torn, it takes some of the cortical bone. It's also a nice representation of interarticular joint degeneration. Rough, irregular bone inside a joint on an ultrasound image, DJD. Various forms, we can talk later on about symmetric, asymmetric, narrowing of a joint relative to the various arthritic conditions, but that's a nice representation of it right here.